we have a sketch of a normal distribution. Notice the horizontal axis is labeled with X. X stands for random variable. Remember that a random variable is any variable we have that's happening at random. For example, the heights of men may have been collected in a column in a spreadsheet. That is a random variable. This random variable specifically, though, must be quantitative. It must be numeric. And notice the smooth curve going across this horizontal line. It must be continuous. So something like heights, including decimals, would be very appropriate here for this random variable. Notice the shape. The normal distribution makes a symmetric bell shape that is unimodal. This means it has one bump in the center. Also notice on the edges of this graph, where I've just shaded, that this graph goes out forever to the left and forever to the right, where the smooth line never touches that random variable x's axis. This is important because we say that the total amount of area under this curve is 100%. And the area under the curve is representing the probability of something occurring. So we're saying it's not impossible. If something actually is included as a possibility at all, we would never say it's exactly 0% likely, because the tails of this curve continue. So again, the random variable x is continuous. In the center of this distribution, we have the mean. Mu, if we are talking about the population mean. This is the true population mean. Whenever we have a symmetric distribution like this, the mean is very nice. It does take into account every single value, so the mean is usually very sensitive to outliers. So with something symmetric like this, the mean is going to be right smack in the middle. It will look very nice. Talking more now about this bump on the picture, this unimodal shape, let's think for a second about the idea of a histogram. A histogram has a very similar notion to that of a bar graph, except we're looking at, again, a quantitative variable where left to right the number line has meaning. And the bars, the height of each bar represents the frequency, the count in each bar. On a histogram, because of this continuous characteristic, we like to draw our classes, or our bars, touching. So looking here, and on the left axis, that vertical axis, we can have frequency or relative frequency, which is, we can think, in other words, in terms of percent rather than just simple counts. But the idea is that whenever we have data that if we had graphed it originally as a histogram would have had this bell shape, what we're essentially doing is still thinking about up under that smooth curve quantities or percents, except we are using a smooth line to trace the shape. So here, this tallest bar, that means the highest frequency is right there where mu is. This means that our mode being the highest frequency, is also right in the center because this is a unimodal bump and because it is symmetric. Those two features together tell us that the mean and the mode are lining up together. On the left-hand side of the mean, we have exactly 50%. On the right-hand side of the mean, or the center, we have exactly 50% because, again, we have symmetry. And again, 100% of the items that can occur are up under this curve. It's being represented by the height of this curve, or the area under this smooth curve. So in addition to the mean lining up perfectly with this mode, we have another measure of center called the median, which is a literal measure of center. To calculate a median, we simply take all of the data values, put them in order. Typically people will go ascending, but whatever, as long as they're ordered, and count literally to the inside of the data. The median is great for going to that exact center place. If there's two values in the center, you would average those two to get right to the midpoint, right? And this right here is a nice measure that is not as sensitive to outliers. On the normal distribution, notice that all three measures of center line up together. This is a very nice feature because it means that we have flexibility. We can use the mean in a lot of calculations without worrying about its sensitivity to outliers. We can also move on to things like box plots where we choose to use the median and the IQR, and those can still have good meaning for us. So remembering that these bars, the height of those bars that count, represents some quantity. And while this percent's not going to be truthful at all, the idea behind getting the percent of the bar would be to take the count. Let's say the count is 6. And let's pretend that the total number of items is 10. Again, that's not realistic for this drawing. I'm just demonstrating how percents can be found, okay? So if we said the sample size is 10, the percent in that zone right there that I shaded purple would be 6 divided by 10, 60%. This is how the conversion happens. We're looking at the balance of the real data, and then we're shading and saying, oh, I can convert this thinking to relative frequency, to percentages, and we are not losing any value of meaning. In fact, maybe it's more meaningful if we would like to discuss the probability of something in that zone, in that class or interval occurring. Again, be reminded that we have 100% under this curve. We're looking at the area under the curve for probability. Also, it's important to remember that with probabilities, we know things such as that a probability can never be negative. Probabilities, if you're thinking in percentages, will go between 0 to 100%. Or if you're thinking about them in decimal form, they go between 0 to the number 1. But again, we never get negatives, and the area under the curve is 100%. So these little bitty tails that I've just now highlighted, those do have some probability, even if it's minimal, of occurring. Let's talk now about something called the empirical rule. This empirical rule can also be referred to as the 68, 95, 99.7 rule. And there's a prerequisite for applying this approximate type of trying to think about area corresponding to parts of our distribution. The prerequisite is that we have an approximately normal distribution. And then given that we have this approximately normally distributed distribution, we are able to look at the standard deviation. Standard deviation tends to go along with the mean. Standard deviation means the average deviation, the average distance from that center, that mean. So basically the distance of every single value from the center, from the mean, is averaged. So what we can say is approximately 68% of our data is going to fall within plus or minus 1 standard deviation of the mean. I'm using SD here to stand for standard deviation. Technically, sigma is when we're talking about a population, but I'm going to keep this a little bit more vague and use SD for standard deviation. Because with empirical rule, we are sometimes looking at real life data and using things like approximately normal and trying to kind of think in our minds about what that would mean with the standard deviations that we may have from a sample. Next, we have approximately 90% of our data. Next, we have approximately 95% of our data within plus or minus 2 standard deviations of the mean. And lastly, we have 99.7% within plus or minus 3 standard deviations. Please notice that 99.7% is very close to 100%. However, it is not 100%. Again, notice those highlighted tails on the picture. We say that is continuing forever to negative, to positive side of the graph, and so we are never going to say we have 100% captured. Let's look at this problem here, example 1 from your text. IQ scores at Stanford Binet, IQ scores of the Stanford Binet scale. The distribution is known to be normal within, which N, the capital N like that stands for normally distributed, right? So within of 100, 16. So whenever we're using this notation, we use N, left parenthesis, the mean, mu, that's 100, comma, standard deviation, sigma, and then right parenthesis. So that's a condensed way of giving you the information about a normal distribution. So let's take this back to the picture we've been looking at. And let's think about how we could sketch out what is occurring on these IQ scores. So again, we have a normal distribution. We know the mean was 100, the standard deviation was 16. In the center of the curve, we can then label mu to be 100, and we also know that that means the median is 100 and the mode is 100. But all we need right now is 100 as that IQ score, since we're using mean, which likes to go along with standard deviation, since standard deviation was again calculated from the average distance from the mean. So the first standard deviation, this picture is not drawn to scale at all, okay, so please be tolerant of this being a rough sketch. Technically, the first standard deviation will actually occur at the inflection point on the graph. There's actually two inflection points on the left and the right. That's where the concavity is pointing up. It's where the rate of change, basically it changes from having that concave up to beginning to be concave down. So looking at that inflection point where we can say, hey, the concavity is about to change. I'm not drawing it perfectly here, but I'm trying to kind of represent it. So the inflection point being where the concavity changes, we would say, hey, technically that's where one standard deviation would be. And I probably should have moved these lines in a little closer to the center, but again, that's the theory if you were actually being very meticulous with your picture. To label these values, I'm going to say the mean 100 plus 16, 100 subtract 16. So essentially when I'm drawing a picture using standard deviation, what I will do is I'll take the mean and manually add and subtract the standard deviation amount. This is just if we want to get kind of a rough picture of what this looks like. So within that plus or minus one step size or standard deviation from the center, we have approximately 68%. So 68% of our IQs is thought to be between 84 to 116 for the IQ score. If we had gone two standard deviations above and below, so let's take 116 and add 16, 184, subtract 16, let's get that extra step. Again, not to scale, thank you for not getting too hung up on that, hopefully, as you're watching this. Adding that gives us the next step out in each direction. We have approximately 95% of our IQ scores are going to fall within these two values. So we would say it's 95% likely that a random person would be between a 68 to a 132 for their IQ score. 95% likely. That's pretty likely. In fact, as statisticians, we tend to use 95% as a good measure for something that should be usual, because I mean that's pretty large. We say that if something is in that 5% zone, then it's considered to be unusual. So anything beyond lower than 2 standard deviations to the left, higher than 2 standard deviations to the right, things beyond those 2 standard deviations would be called unusual because they're falling in that 5% area or probability. We can actually use the symmetry of this picture too to think about exactly how much area is in the tails of this picture. Right? Because if we have 95% in the center here and we know we have 100% total under our curve, what we can do is we can say 100% subtract 95% to consider how much area is not being included in the center, and that gives us 5%. Then, remembering that this is a symmetric distribution, we simply divide that leftover percent, that 5%, equally. We divide it by 2 to share it equally to both tails. So 5% divided by 2, that will give us 2.5% in each tail of this distribution when we're looking beyond plus or minus 2 standard deviations. Okay, so now let's add 16 to that 132 and subtract 16 to the 68. Now we're showing 3 steps below the mean, 3 steps above the mean. So this is within the plus or minus 3 standard deviations. We have that 99.7% of the people found at random would be between these two values. And again, we can use the same reasoning to get the area in the tails if we would like. Here we have 100% subtract 99.7%. That gives us 0.3% when we from subtracting. And then we can divide that by 2. So we're getting, if we wanted to write this in decimal form, that's actually 0.0015 if we were thinking between the 0 to 1. Okay, now for example 2. A charity group proposes sandwiches for the poor. The weight of these sandwiches are distributed normally with mean of 150 grams and standard deviation of 25 grams. One sandwich is chosen at random. This is a random sample of just that one sandwich. What is the probability that this sandwich will weigh between 145 and 155 grams? See that the mean is at 150. And then taking that 25 as the step size, that standard deviation, we can label plus or minus several steps to the left and right. So what we can notice here, though, is that these values of 145 and 155 are not falling perfectly on any of these lines. So the empirical rule really doesn't come to help us that much. It can give us some reasoning about the distribution. I put little stars there about where those would be. So they're within one standard deviation, it looks like, below and above the mean. So actually quite common, right? But we know it's a little bit less than that because we are making this more narrow. You know, we can also talk about something called the z-distribution. The z-distribution, or we could also call this the standard normal distribution. So it's very easy to talk about things on this standard scale where the center is exactly 0 and a positive 1 means one step above, a negative 1 means one standard deviation one step below that mean. So we can go back and talk about the same balance of heights on a standardized scale. So to give you an idea of what these values would look like, let's go ahead and normalize the 145 and the 155. If I take 145 as my value that I would like to standardize or normalize, I take that, subtract the mean of 150 divided by the standard deviation of 25. So we are actually even less than 1/3 of a step away from that center. The negative meaning that value, the 145, is less than 1/3 of a step below the average. Let's now standardize the 155. 155, subtract 150, the mean, divided by 25. So now let's go and look back at the text and remember that you do have some Excel commands that can help you with finding probabilities. So we didn't get the exact probability, the exact answer on that last example. So looking at your text, notice again that there's some commands you can use. They're a little bit tedious, but you can use them. Also, I have for you an Excel workbook designed by Z. Arnholt, a professor at Appalachian State University. And she programmed this for us so that we are able to find areas easily. And actually there's other tabs across the bottom of this worksheet that you may appreciate for different things that we will go over in the stats class. But the nice thing is, as long as you only type in the highlighted boxes, and the highlighted boxes actually match the pictures with color too, the formulas for using that normal distribution are already keyed in for you. So this is a pretty handy Excel spreadsheet to have. So here let me put mu in, the standard deviation, and this. And then you'll notice that I have 3 different sections that I can use. I have less than, that's the mint green on the picture. If I want to type something in there, I'll be finding the area or the probability of being less than that value. I have in between, that's the blue picture, notice it corresponds. And then the purple shows me here, that's area greater than some value. So this really does make it so we don't have to go through all of those operations by hand. And again, when I click on this, you can see that the formula that's in your text, on the online text, that has been used. You can see that up there on the ribbon for the equal to and the formula. Using in between, let's type those values in. Okay, and there we have it.